The Japan Meteorological Agency recorded a magnitude 6.3 earthquake striking off the coast of Miyagi Prefecture in Japan's region at a depth of 50 kilometers below the seafloor, with the epicenter positioned approximately 50 kilometers offshore. Within minutes, the entire Shinkansen bullet train line, the spinal column of high-speed rail connecting Tokyo to Shinomori across 674 kilometers of northeastern Japan, was suspended by JR East for emergency safety inspection. Shindo lower 5 intensity was registered in Ishinomaki, Tome, and Saki in Miyagi Prefecture, and the tremors, which propagated southward along the full length of Honshu, were felt as far as Tokyo itself, where residents experienced Shindo level 2 mild shaking, but shaking nonetheless, 370 kilometers from the rupture point. This is not a story about an inconvenience. This is a story about what that rupture point means, what it sits above, and what the instruments now accumulating data along the Japan Trench are telling the scientific community on this precise day in May 2026. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: the Japan Meteorological Agency, the United States Geological Survey, JR East's official operational communications, the Smithsonian Global Volcanism Program, NOAA, and peer-reviewed research published through institutions including the Incorporated Research Institutions for Seismology and the Earthquake Research Institute at the University of Tokyo, but official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us, but that is not even the complete picture, because what a magnitude 6.3 earthquake off Miyagi's coast represents in isolation a strong tremor, a precautionary rail suspension. A Shindo lower 5 measurement in 3 cities is only the visible surface of a geological system that has been accumulating energy for decades, that has already killed thousands in this exact geography, and that is operating under conditions today in the spring of 2026 that scientists choose their language carefully to describe. The May 15th earthquake did not occur in isolation. It occurred within a seismic sequence that began building in November 2025, in a subduction zone that produced one of the 4 most powerful earthquakes ever recorded on this planet in 2011, in a fault system that has been producing catastrophic ruptures along the Sanriku coast of northeastern Japan since at least 869 AD, which is not the beginning of that system's activity, merely the beginning of the written human record of it. The question before us today is not whether this coastline is at risk. The geological record settled that question long before any of us were born. The question is what the instruments are showing right now, what they showed 27 days ago when a far larger event struck the same fault family, and what that combination tells us about where the system sits on the accumulation curve. The system is not inactive, it is accumulating. To understand what happened at 2022 JST on May 15, 2026, it is necessary to stand at the edge of the Japan Trench and look down, not metaphorically, literally in the physical sense. The Japan Trench is a submarine canyon that stretches approximately 800 kilometers from the Kuril Islands in the north to the Izu Islands in the south, and at its deepest point it descends to 8046 meters below the surface of the Pacific Ocean, that is 8 kilometers of water column pressing down on a geological boundary, where 2 of the largest tectonic plates on Earth are locked in a collision that has been ongoing for millions of years. The Pacific Plate, an oceanic plate that underlies much of the northern Pacific, is subducting, driving itself westward and downward beneath the Okhotsk microplate at a convergence rate that the USGS and the Japan Meteorological Agency have both measured at between 7, 9, and 9, 2 centimeters per year. 9 centimeters per year does not sound like much. Hold your hands apart by 9 centimeters. That is approximately the width of your palm. Now imagine that the object moving that far each year is not a hand but an entire tectonic plate, a slab of oceanic lithosphere, hundreds of kilometers wide, tens of kilometers thick, and carrying every ocean basin, seamount, and sediment deposit above it down into the mantle of the Earth at a shallow angle, 9 centimeters per year. Every year, for millions of years, that is the force the Japan Trench is containing. And what the instruments along the Sanriku coast have been recording since late 2025 is what happens when the sections of that system that have been locked, held in place by friction between the 2 plates, begin to slip. On May 15, 2026 at 2022 JST, a section of that system slipped again. Magnitude 6.3, depth 50 kilometers. The Japan Meteorological Agency issued its emergency earthquake warning for the region within seconds, a system that uses the faster-moving P waves from the initial rupture to send alerts to smartphones, television broadcasts, and railway control systems before the more destructive S waves arrive. JR East received that alert, assessed the situation, and suspended the Shinkansen between Tokyo and Shinomori stations immediately. This is standard protocol in Japan. It is also, when examined from the outside, a remarkable window into how seriously the engineering and operational infrastructure of this country takes the seismic environment it exists within. Bullet trains that operate at 320 kilometers per hour across viaducts and bridges spanning fault-prone terrain do not simply slow down. When an earthquake warning arrives, they stop completely. And every centimeter of track between Tokyo and Shinemori, every viaduct, every bridge bearing, every overhead wire support along 674 kilometers of high-speed corridor must be physically inspected before a single passenger train moves again. JR East completed those inspections by approximately 22:40 JST on May 15th, less than 2.5 hours after the rupture, and the Shinkansen resumed service. Some trains on the Yamagata Shinkansen remained suspended beyond that point. There were no reports of injuries, there were no reports of structural damage. And yet the absence of immediate injury does not mean this event can be filed and forgotten. Here is where this account becomes genuinely significant. The magnitude 6.3 earthquake of May 15th is the largest earthquake to strike the region since April 20th, 2026, 27 days earlier, when a magnitude 7.7 earthquake struck off the Sanriku coast at a depth of 35 kilometers, issued an immediate tsunami warning from the Japan Meteorological Agency for the coastlines of Iwate, Aomori, and Hokkaido, halted the Hokkaido, Akita, and Shinkansen lines simultaneously, triggered evacuation orders for 82,811 households encompassing 175,957 people across 13 cities, 21 towns, and 6 villages spanning 5 prefectures, and prompted the Japan Meteorological Agency to issue a rare subsequent earthquake advisory warning of elevated risk of a follow-on magnitude 8 or greater event through April 27, 2026. The jma calculated that following the April 20th event, the probability of a magnitude 8 or larger earthquake in the Japan Trench zone in the following days rose from its background level of approximately 0.1% to approximately 1%, a tenfold increase in the likelihood of a catastrophic event. 1% sounds small in the language of seismic risk. A tenfold increase in megaquake probability concentrated over a short window following a major precursor event is not small. It is exactly the pattern that preceded the worst seismic disaster in Japan's modern history, and the scientists who issued that advisory in April 2026 know that history in precise detail, because this has already happened once, and the record of it is still preserved in the rock in the sediment cores of the trench floor, and in the official death registers of Miyagi and Iwate and Fukushima prefectures, where the toll is still counted. The question is not whether, the question is when. On March 11, 2011, at 14:46 JST, a magnitude 9.029, one earthquake ruptured the Japan Trench subduction interface in the same fault system that produced the April 20th and May 15th, 2026 events. That rupture area stretched approximately 450 kilometers in length and 150 kilometers in width. The maximum fault displacement, the actual physical movement of one plate against another along the rupture surface, was estimated at between 30 and 40 meters. 30 meters, the height of a 10-story building, moving in a single geological instant, compressed into a rupture duration of approximately 150 seconds. That displacement pushed the floor of the Pacific Ocean upward and outward, generating tsunami waves that struck the Sanriku coast of. With run-up heights that overran sea walls designed to withstand 10-meter waves in Iwate and Miyagi, that reached 38 meters in some locations, and that inundated 73 square kilometers of the city of Ishinomaki alone, the city whose name appeared in the official Shindo reports from May 15, 2026, as registering lower 5 intensity, Ishinomaki. A coastal fishing city at the head of Ishinomaki Bay at the mouth of the Kitakami River, the second largest city in Miyagi Prefecture, home as of mid-2025 to approximately 131,189 people. In 2011, Ishinomaki was the single municipality in all of Japan with the highest confirmed death count from that tsunami. By June 2011, 3,097 confirmed deaths had been counted there alone. A further 2,770 people were unaccounted for. The earthquake shifted the city physically southeast and downward, lowering ground level by as much as 2 meters in some areas, enough that tides began flooding land that had previously been dry. The tsunami inundated 73 square kilometers of that city's land area. 20,044 homes were completely destroyed. 13,049 were partially destroyed. The nationwide toll of the 2011 earthquake and tsunami, as reported by the Japan National Police Agency, reached 15,836 confirmed deaths, with 3,664 people still reported missing. The World Bank estimated the total economic loss at up to $235 billion, the highest economic loss from a single natural disaster ever recorded at that time. Think about those 131,189 people living in Ishinomaki today. They rebuilt. They returned many of them, though not all, because 26,281 people across Fukushima Prefecture alone remained classified as designated evacuees as recently as March 11, 2026, the 15th anniversary of the disaster, still unable to return to homes that remain under evacuation orders due to nuclear fallout. From the Fukushima Daiichi plant that lost 3 reactors to the tsunami, the people of Ishinomaki who stayed or returned built new sea walls, they built elevated roads, they built tsunami evacuation towers, they planted memorial groves, they opened the Miyagi 3.11 Tsunami Disaster Memorial Museum at Ishinomaki Minamihama Tsunami Memorial Park, a circular building with transparent glass walls, allowing a view of the ruins of Kadanowaki Elementary School, where children died. And on the evening of May 15, 2026, when those same earthquake alert tones sounded across their smartphones and televisions at 2022 JST, those residents felt Shindo lower 5 intensity shaking, strong enough for most people to feel genuine fear, according to the official Japan Meteorological Agency description. Of that intensity level, strong enough for dishes and books to fall from shelves, strong enough to challenge pedestrians and drivers, strong enough for anyone who was in Ishinomaki on March 11, 2011, to reach directly into the body's deepest memory and ask the same question that was asked then. Ask yourself what question that would be. You already know the answer. It is the only question that matters on a coastline that has been struck by catastrophic tsunamis driven by this exact fault system in 869, in 1896, in 1933, and in 2011. The question is not about magnitude. The question is, how much time do we have? The 1933 Sanriku earthquake is the historical anchor that every seismologist studying this coastline keeps in the room when they discuss the May 2026 sequence. On March 3, 1933, at 2:31 in the morning local time, a magnitude 8 for earthquake struck the Pacific Ocean approximately 290 kilometers east of Kamaishi in Miyagi Prefecture. This is not a hypothesis. This is documented in the geological record and generated a tsunami that struck the Sanriku coast, with waves reaching 7 meters in height near Ryori and Kisen, Iwate. The tsunami killed over 3,000 people along the coastlines of eastern Honshu. It destroyed thousands of homes. It inundated fishing villages that had still been rebuilding from the 1896 Meiji Sanriku tsunami, which had itself killed 22,066 people. The people of Sanriku in 1933 had lived through a prior catastrophe. They understood the threat in the abstract. And yet the waves that came that morning at 2:31 in the darkness in March, while fishing communities slept, outpaced many of the evacuations that history and prior experience had told those communities were possible. Eyewitnesses recorded hearing a roaring sound from the sea 10 to 15 minutes after the initial shaking. And then the first wave arrived, followed by larger surges. The ground shaking in 1933 was not particularly severe at the coast. It was the tsunami that killed. The earthquake and the tsunami are not the same threat. They arrive in sequence, separated by minutes that are not hours, and in this context, that difference is everything. This is not a hypothesis. The Japan Trench has produced this pattern: large offshore rupture, minimal local shaking, catastrophic tsunami multiple times in recorded human history, and the sediment cores drilled from the trench floor by the Integrated Ocean Drilling Program's Expedition 343 in 2013 contain the evidence of events extending far beyond the written record. Those cores revealed the frictional properties of the plate boundary fault zone, specifically that the shallow portion of the subduction interface is composed of clay-rich material with very low friction at coseismic slip velocities. What that means in practical terms is that when the deep, locked portion of the fault ruptures, the slip propagates all the way up to the trench, all the way to the seafloor, because there is almost no friction to arrest it. That is what happened in 2011. The maximum coseismic seafloor displacement in 2011 was 30 to 40 meters, and it extended to the trench itself, which is why the tsunami was so large and why the seawalls that had been designed based on historical data up to that point were overwhelmed. Before 2011, Japan's seismic hazard models set the maximum credible earthquake along that section of the Japan Trench at magnitude 8.3. An earthquake almost a full magnitude unit larger and in moment magnitude, each full unit represents approximately 32 times more energy released arrived instead. The models were wrong not because the science was bad, but because the historical record was insufficient. The absence of a mega earthquake in the written record is not evidence that a mega earthquake cannot occur. The 2011 earthquake proved that conclusively at a cost of 15,836 confirmed lives. The April 20, 2026 magnitude 7 for earthquake, the event that preceded the May 15th magnitude 6.3 by 27 days, was studied in this context by the global seismological community with considerable attention. The USGS finite fault model for the April event estimated a rupture area of 70 kilometers by 65 kilometers, with a maximum slip of 735 meters near the hypocenter, a USGS seismic installation at Amori recorded peak ground velocity of 15.01 centimeters per second. A second installation at Morioka, Iwate, recorded peak ground acceleration of 0.400 for grams. The global centroid moment tensor assigned the earthquake a moment magnitude of 7.5. The Japan Meteorological Agency's preliminary magnitude was 7.7. Tsunami waves did arrive at the coast. Wave heights maxed out at 80 centimeters, well below the 3-meter forecast, and the threat resolved without casualties. But the scientific advisory that followed was carefully worded. The GMA stated publicly that the likelihood of a new, large earthquake occurring was relatively higher. Then during normal times, a spokesperson chose language deliberately, the language of calibrated scientific caution, and that careful language is itself the warning. Scientists who study subduction's own seismicity are aware that major earthquakes in this fault class can act as foreshocks to larger events. The clearest example in the record for this specific fault system: on March 9, 2011, a magnitude 7, 3 earthquakes struck the Sanrikuoki zone. 2 days later, on March 11, 2011, the magnitude 9.0 earthquake ruptured the same system. This is not a prediction that history will precisely repeat. It is a documented fact about the behavior of the Japan Trench subduction zone, and it is the reason the jma elevated the megaquake advisory following April 20th, and it is the reason the May 15th magnitude 6.3 event occurring 27 days after that advisory cannot be treated as simply a smaller, quieter afterthought. The system is not finished speaking. There is a second dimension to this account that operates on a different scale of time entirely. The Japan Trench fault system does not exist in isolation. No tectonic system does. Japan sits at the convergence point of 4 tectonic plates, the Pacific, Philippine Sea, Eurasian, and Okhotsk. The convergence rate at the Japan Trench alone 7.929 2 centimeters per year means that over the course of a century, the Pacific plate advances nearly 9 meters relative to the Okhotsk plate above it. In sections of the fault that are locked held by friction, that 9 meters per century is not released gradually as a seismic creep, it is stored. It accumulates an elastic strain in the rock of both plates, and it will eventually release the 2011 earthquake released accumulated strain equivalent to 250 kilometers of rupture length and fault displacements of up to 40 meters. Even after that enormous release, the post-seismic deformation, the viscous relaxation of the mantle, and the afterslip of the fault continued to be recorded by GPS stations and seafloor observation networks for years afterward. As of the research published through science and peer-reviewed journals studying the fault a decade after 2011, trench normal extension remained detectable in the oceanic plate. The system had not returned to its pre-2011 equilibrium, it was continuing to adjust. Now add the dimension of solar activity and its relationship to terrestrial seismic stress, a connection that remains an area of active research rather than settled consensus, but that the long-view thinker cannot responsibly ignore. The current solar cycle 25, has exceeded initial forecasts of activity in both flare frequency and geomagnetic storm intensity. Extreme ultraviolet and X-ray flux from elevated solar activity modulates the ionosphere, affecting GPS accuracy, including the GPS networks that Japan's earthquake early warning system and the NEEDS seismic station network rely upon for precise hypocenter determination. Separately, research examining correlations between atmospheric pressure loading, tidal forcing, and fault slip behavior in subduction zones has documented that external forcing, including tidal loading cycles, does modulate the timing of small slip events along fault zones already close to failure. This does not mean that solar activity causes earthquakes in a direct mechanical sense. What it means is that the Earth's crustal stress field is not sealed from external influence, and that in a fault zone already loaded to high levels of accumulated strain, any additional forcing mechanism, tidal, atmospheric, thermal, is worth monitoring in conjunction with the seismic record. What the official data actually shows is a fault zone in northeastern Japan that has been producing large earthquakes continuously since November 2025, a foreshock sequence preceding the April 20th event that included 162 earthquakes above magnitude 4.0 and 5 events above magnitude 6.0 followed by a magnitude 7 for 2.7 main shock, followed by an elevated megaquake advisory, followed by the May 15th magnitude 6.3 event 27 days after the main shock. That sequence, in its totality, is what seismologists mean when they say that the system is accumulating. Now stand in Kesennuma. It is a city in northern Miyagi Prefecture at the head of a deep ria inletted round river valley on the Sanriku coast with a current population of approximately 60,000 people. It is a fishing city, which means it is also a coastal city, which means its waterfronts, its fish markets, its harbors, its older residential neighborhoods built on low ground at the water's edge are within the tsunami inundation zone mapped by the Japan Meteorological Agency based on what happened in 2011, Kesennuma. Registered Shindo 4 on May 15th from the magnitude 6.3 event. Shindo 4 is strong enough to wake sleeping people, strong enough to rattle windows and hanging fixtures, strong enough for people to seek cover. And across Kesennuma on that evening, in the 37 seconds between the initial P-wave detection and the full arrival of shaking, every smartphone and television in that city issued the earthquake warning tone, a specific electronic sound designed to penetrate consciousness even from sleep, and every person in Kesennuma who heard it made a calculation, mostly subconsciously, mostly instantaneously, about whether to run for higher ground. Most of them did not run. The shaking was strong but not catastrophic. No tsunami warning was issued, and by 2240 JS the Shinkansen was running again and the news cycle had moved on. But the 60,000 people of Kesennuma carry in their bodies a knowledge that does not move on. They rebuilt their sea walls. They know exactly where the high ground evacuation routes go. They know how many minutes they have between a large offshore rupture and the arrival of the first wave, and in the spring of 2026 they are living through the most seismically active period in the region since 2011 itself. Ofunato, in southern Iwate Prefecture, registered Shindo 4 in the May 15th event. Ofunato is a coastal city of approximately 33,000 people. It was struck by tsunami run-up of 9.3 meters in 2011. It was specifically named in reports citing the USGS measurement of the May 15th earthquake as epicentered. Near its coast, these are not abstract numbers assigned to uninhabited geology. These are addresses. These are fishing boats in the harbor. These are schools and clinics and morning markets. These are the people who, when they feel Shindo 4 on a Thursday evening in May, check their phones, check the jma website, and wait the specific practiced, disciplined, deeply human act of waiting to see whether a tsunami advisory follows. On May 15th, it did not, but the waiting itself, the pause between the shaking and the all clear, is the measure of what this coastline holds inside every waking moment. The Japan Meteorological Agency's earthquake early warning system, operational since 2007, detects the initial P waves from a rupture and broadcasts alerts to television, radio, smartphones, and railway control systems within 5 to 10 seconds before the more destructive S waves arrive in a major offshore rupture generating. A tsunami, that warning system buys minutes, not hours, minutes. The difference between life and death on the Sanriku coast in a tsunami scenario has historically been measured in whether people moved immediately, before the shaking stopped, before the all clear, before the visual confirmation of the sea receding, which is itself a tsunami warning sign of the last possible kind, in 1933. People saw the sea recede after the earthquake and they ran. Some of them were outpaced by the wave. Minutes are not hours, and in this context, that difference is everything. Japan's response infrastructure is among the best on Earth. Building codes revised after every major earthquake, base-isolated structures, gas systems that automatically shut off at Shindo 5, annual national disaster drills, dense seismic monitoring networks operated by the National Research Institute for Earthscience and Disaster Resilience, including the SNet and DONET systems of seafloor, sensors stationed directly above the Japan Trench and Nankai Trough subduction interfaces. The government spent decades and hundreds of billions of yen building seawalls along the coast following 2011. Seawalls 12 meters high in places where the 2011 waves reached higher than that, the Onagawa nuclear power plant in Miyagi Prefecture, the Fukushima Daiichi and Daini plants, the Plantine Mori all reported no abnormalities following the April 20th magnitude 7. For event or the May 15th magnitude 6.3 event, the engineering works, the warning systems work, the protocols work, and yet the scientific community, when it speaks carefully and honestly about this fault system in 2026, does not use the word safe, it uses the word prepared. There is a difference that matters enormously, and the difference is this: preparation is a human act, performed in response to a geological reality that preparation does not alter. The Pacific Plate is still moving at 9 centimeters per year, the locked sections of the Japan Trench are still accumulating strain, the fault properties that enabled a 40-meter slip in 2011 have not changed. What has changed is that the instruments now positioned along the trench, the seafloor pressure gauges, the ocean bottom seismometers, the GPS baselines, the dense HyNet and KNet sensor arrays across Honshu give scientists and emergency management agencies a resolution of situational awareness that was not available in 2011. The monitoring is in place and detection is possible, but prediction is not. That sentence spoken by the scientists who operate this network is not a failure. It is the most honest thing seismology can currently offer. The foreshock sequence that preceded the April 20th, 2026 magnitude 7 for event began in November 2025. It produced 162 earthquakes above magnitude 4. 0. It produced 5 earthquakes above magnitude 6, 0, the strongest of which reached magnitude 6, 8. In December 2025, a separate magnitude 7, 6 earthquake struck approximately 140 kilometers north-northwest of the April 2026 epicenter. The seismic sequence that includes the May 15th magnitude 6, 3 event therefore sits within a broader envelope of activity that has been building for at least 6 months across the northern Japan Trench system. By April 23, 2026, 3 days after the main April event, 17 aftershocks of magnitude 4, 0 or higher had been recorded, the strongest at magnitude 5, 6. The May 15th magnitude 6, 3 is now the largest event in the ongoing sequence since the April 20th main shock. Whether it represents the tail of that sequence diminishing or an independent loading event on an adjacent fault segment is precisely the question that the scientific community cannot yet answer with certainty. What the instruments show is continued activity. What the accumulation of verified data from the Japan Meteorological Agency, the USGS, and the NEED shows is that the Japan Trench remains in an elevated state of seismic expression. The advisory period may have officially ended on April 27th. The Earth's geological calendar does not observe advisory deadlines. The 2011 earthquake shifted the figure axis of the Earth itself by approximately 17 centimeters and shortened the length of the day by 8 microseconds. Those are not dramatic numbers in human terms. In geological terms, they represent a planetary body physically redistributed by a single 1/50-second rupture event along a submarine fault. The Earth's axis moved, the length of the day changed. 450 kilometers of fault boundary moved by up to 40 meters in under 3 minutes, and 15 years later marked precisely on March 11, 2026, with moments of silence across. At 14:46 in the afternoon, 26,281 people in Fukushima Prefecture remain designated evacuees, unable to return to homes that still sit within nuclear contamination zones. The recovery from 2011 is not finished. It will not be finished for decades, and against that open wound in the landscape of northeastern Japan, the Japan Trench continues to accumulate, the Pacific Plate continues to drive itself westward at 9 centimeters per year, the May 15th magnitude 6. 3 event registered Shindo Lower 5 in Ishinomaki, where 3,097 people were confirmed dead in 2011 and halted the Shinkansen for 2 hours and 18 minutes and generated no tsunami and caused no reported injuries, and by the following morning had largely disappeared from the news cycle of a world with many things demanding its attention. The instruments along the Japan Trench did not stop recording. They recorded through the night of May 15th, they recorded through May 16th, as of the morning of May 17th, 2026, they continue to record every tremor, every slip, every whisper of motion along the boundary where a 9 centimeter per year geological collision has been building pressure since before the first human civilization placed its foundations in soil. The question that the people of Ishinomaki and Kesunuma and Ofunato and every coastal city on the Senriku coast carry in their bodies every day, the question they felt again on the evening of May 15th when the alert tones sounded and the shaking began, is the same question the instruments are asking in the precise language of seismic waveforms and ground velocity measurements and moment tensor solutions, without pause, without rest, in the dark water above the deepest trench on Earth's Pacific margin. The answer has not yet arrived, but the instruments record the question continuously, in the only language the Earth actually speaks, which is movement and pressure and the slow, inexorable conversation between plates that has been underway for longer than our species has had words for it.